Hi, this is Mr. Barron, and what we're going to be doing is we're going to be talking about something from Chapter 4, which is, of course, aqueous solutions and the reactions that happen within them. An easy way to remember the type of reactions that occur within aqueous solutions is the acronym RAP. R stands for redox. A stands for acid-base. P stands for precipitation. This presentation that I'm going to be giving you is on redox because that's the most challenging to occur or to understand. Precipitation, you just need to memorize your solubility rules to be able to predict which compound will be insoluble and precipitate out. So the couple things that you need to know are solubility rules, and you also need to understand net ionic equations to be able to describe it. And we can write those net ionic equations for precipitation reactions and also for acid-base reactions. Acid-base reactions, what you need to know is that primarily they produce, when you add an acid to a base, you produce a salt and water. Now for redox reactions, it involves electron transfer, so it's a very different type of reaction. So redox stands for reduction and oxidation. An easy way to remember what's happening with reduction and oxidation is the mnemonic oil rig. Oil, oxidation is loss, so it's a loss of electrons that it's describing. And reduction is gain. Reduction is gaining electrons. It's an easy way to remember it. If you look at the periodic table, and I'm going to draw a very quick, not very accurate periodic table at all actually, but I'm just going to draw a quick one. You know, you have that zigzag line that makes the divide between the metals and the non-metals. Don't forget the metals are on this side and the non-metals are over here. Don't forget metals typically are oxidized. And an example of something being oxidized, a metal being oxidized, would be calcium losing 2 electrons and forming a positive 2 charge. Reduction, for things that are reduced, a good example of something that's been reduced is oxygen gaining 2 electrons and having a -2 charge. So that's an example of redox reactions. Now to understand who's gaining and who's losing electrons in a redox reaction, we have to be able to assign something called oxidation states. Now oxidation states also goes by the name oxidation numbers. You'll see it used both ways depending on the textbook that you're in or the professor that you have in college. In my class, you'll hear me use both so that you can get comfortable with it. And I want you to understand that oxidation states and numbers, we're going to do some problems from 4.49 in your textbook. Oxidation states, I really want you to know the numbers are imaginary. They're not necessarily real charge. And because they're imaginary, the only purpose that they serve, the purpose is to identify, and I'm just going to put purpose is to ID how electrons are transferred, to see where they're coming from and where they're going to. So I'm just going to put trans. Now, let's look at a problem in 4.49. Let's look at S in SO2. Now there's a handout that I think is going to be very helpful that I helped write for you guys. This is the handout. I'll be passing it out in class, and it's right now available in the handout section of my website, and you can actually print this off. I think this explains the rules for assigning oxidation states much better than our textbook. Now one of the most important rules is that oxygen always has a -2 charge in covalent compounds. Well, this is a covalent compound because there are both nonmetals, and let's write out what the oxidation state is for just one oxygen. I'm going to write it above. For just one oxygen, it's -2. But since I have 2 of them, -2 times 2 has to be 4, a -4 charge. So then the question becomes, what does the sulfur have to be to balance out the -4 charge? Well, the answer, of course, is +4. So the charge, the oxidation state, which is an imaginary charge, for sulfur is +4. Now we're going to do another example. This time we're going to do it for a compound that actually does have an overall charge. So MnO4 negative. And I want to know what the oxidation state is for the manganese. So again, we know that oxygen has a -2 charge. We have 4 of them. If I have 4 of them, that means that I'm looking at a charge of -8. So then the question becomes, what has to be the charge of manganese such that when I add it to the -8, it will give me the overall charge for the compound? If you're thinking that it's 7, you are correct. And 7 for manganese, +7, is its oxidation state. Let's look at another example. Let's look at, let's see here, AS4. Let's try and find the oxidation state for this. And you should, off the top of your head, be thinking 0, because that's rule number 1. Anything that's by itself, meaning something like an element like sodium, potassium, mercury, silver, or any of the diatomics from Hofbrinkel, hydrogen, nitrogen, oxygen, chlorine, fluorine, bromine, iodine, they are all going to be 0. Now, let's actually take this knowledge of oxidation states and apply it to solve some problems. Let's take a look at problem 4.51. 4.51 has us try and identify who is being oxidized and who is being reduced. I'm going to do A with you. So for A, it shows that solid nickel is reacted with chlorine gas to produce nickel chloride, NiCl2 solid. Alright, I have to figure out who is reduced and who is oxidized. I have to label all of the oxidation states. So nickel is by itself, 0. Chlorine's by itself, it has an oxidation state of 0. Chlorine is -1 typically. Most of the halogens are -1. If you go back to your charges, when you look at it, the monoatomic ion charge for an ion is equal to the oxidation states. So the charge for the chlorine is -1. So if it's -1, I have 2 of them. That means its charge is -2, which means that the nickel has to be +2. Alright, so what this means is that nickel had no charge, and then on the product side, now it has a +2 charge. So it went like this. Nickel all the way to Ni2+. If that's the case, it lost 2 electrons. So in this reaction, nickel, since it lost electrons, think oil and oil rig, is oxidized. Let's look at the chlorine. Chlorine actually gained an electron and formed a negative charge. So chlorine was reduced. Alright, now that's a simple one. Let's do one that's a little bit more complex. The one that I'm going to do now for you is we're going to do, let's see here, let's do B. So for B, we have a big long equation. I'm going to not write out the states of matter. Instead, I'm just going to write out the compounds. So 3FeNO3 2 plus 2 aluminums produces 3Fe plus 2 AlNO3 2. Now I want to show you a shortcut way of figuring this out. So we see aluminum on the left side. We know it's by itself, so it has no charge. Oops, I didn't write it out correct. There's an Al, not an A. We look at it over here, we know it has to have a charge. I know nitrates have a -1 charge. I have 2 of them, so if I have 2 of them, that means I have to have a -2 charge. So, to balance out the -2 charge, what has to happen, oops, another typo, I apologize, or another writing mistake. That's actually a 3, which means if I have 3 of those -1 charges, it's -3. That means aluminum over here is +3. So if it's going from no charge and to a positive charge, it has to have lost electrons. So aluminum in this case is being oxidized. Now I'll give you a hint. if aluminum's being oxidized and you see another metal like iron, then it has to be reduced. So if one thing's being oxidized, the other thing's usually reduced. So we're going to take a look at the iron, which is neutral here. Over here, it has nitrates are negative. I have 2 of them, so it's a -2 charge total. That means my iron has to be +2. So if iron's going from positive charge to neutral, it has to be gaining electrons. So it is being reduced. That's essentially the most information that you need to know about redox reactions for right now. If you guys have any other questions, please ask me individually. Make sure you've taken notes on the podcast and you understand all of the homework sets thus far in this chapter on aqueous reactions.